catalysis development for methanol fuel vehicles, formaldehyde oxidation. Is a contribution by Bob McCade and P.J. Mitchell from the GM Research Laboratories.
This is part 3 in a study of exhaust catalyst development for methanol-fueled vehicles. It deals with formaldehyde oxidation. The previous 2 parts dealt with various aspects of methanol oxidation. And again, I want to acknowledge my co-worker, Patricia Mitchell, and this work was done in the physical chemistry department at General Motors. There's a lot of environmentalists that see methanol-fueled vehicles as an alternative to gasoline, as a clean-burning alternative to gasoline. This fact notwithstanding, there are emissions concerns with methanol-fueled vehicles, chief among which is formaldehyde. It's a major concern both because of its potential health effects and also because of photochemistry. It's photochemically quite reactive. So we felt that this would be something that would be of interest to look at. And before I get into the study, I'd like to point out that there are 2 sources of formaldehyde that can come out the tailpipe of your car if you have a methanol car. One of these is what I call direct, and that's formaldehyde that's produced in the engine by the partial oxidation of unburned fuel. Carries through an exhaust, passes over catalyst unconverted and out into the atmosphere. The other is indirect formaldehyde. And this is produced by partial oxidation of unburned fuel, methanol, over the exhaust catalyst. And in our previous laboratory studies, I focused primarily on this indirect formaldehyde production. And in fact, in this next slide here, I can give you an example of what we see for various catalysts. Here we show results of formaldehyde production over 5 different catalysts. These are all supported on gamma alumina, as are all the catalysts that I will speak about today. A couple things to note. What we're doing here is in the laboratory, we're reacting methanol, CO, and oxygen over these various catalysts and looking at the formaldehyde yield as a function of temperature. What you see here is that the yields of formaldehyde are quite different for these different catalysts. And in fact, this indirect production of formaldehyde can be quite extensive given the large emissions of unburned fuel that are characteristic of these cars. Secondly, you notice that all the curves have a maximum in the formaldehyde production. I think this is indicative of a series-type reaction mechanism where your methanol is first partially oxidized to unburned fuel, to formaldehyde, and then the formaldehyde can further react to form CO2 and water. One of the things we found that 2 of the more attractive catalysts for methanol oxidation were platinum and silver-based catalysts, which, as you can see here, give very low yields of formaldehyde. But this data tells us nothing about the activity of these catalysts for the direct conversion of formaldehyde. And so that was the basis of this additional work that we've done. Experimentally, the direct formaldehyde oxidation is difficult to study because it involves having to make gaseous formaldehyde. And your options are either starting from paraformaldehyde or starting from a formalin solution. Neither one was very attractive to us because of the difficulties of maintaining formaldehyde in a vapor state. So as an alternative, we utilized a pre-reactor to generate formaldehyde by the partial oxidation of methanol. And then we fed that formaldehyde from the pre-reactor into a test reactor where the catalysts were evaluated. And the scheme is shown here. Helium is fed through a methanol saturator, then we add oxygen. It goes up in upflow fashion through a pre-reactor, and then the product stream from that reactor is fed directly into our test reactor. Products from that are analyzed in a normal analysis train. This table shows the composition of the pre-reactor product stream. And at various times in the study, we used 2 different catalysts, one being of palladium, the other vanadium, again, both supported on gamma alumina. In the case of the palladium catalyst, we used that where we wanted to get a stream that contained formaldehyde and really no other oxidizable species. As you can see here, we could generate, starting from about 2.2% methanol, we could generate about 0.02 to 0.025% formaldehyde, 200 to 250 parts per million. On the other hand, by using a vanadium catalyst at somewhat higher temperatures, we could get higher concentrations of formaldehyde, 600 to 750 parts per million. But we also inevitably had CO formed as a product. But this is actually not bad, because in a real exhaust stream you'll always have CO there along with the formaldehyde or whatever organic species you have. Now, what I will show next is I'll gradually put this figure together. I'm going to show results of 5 catalysts, same 5 that we looked at previously for methanol oxidation. And we'll show results of formaldehyde oxidation. But in each frame here, for each catalyst, what I will show will be results of 3 separate experiments. The first involves just the oxidation of formaldehyde, given by the solid curve. The second is the conversion of formaldehyde in a stream that contains both formaldehyde and CO. And thirdly, just for comparison purposes, we show just the conversion of carbon monoxide in a feed that contains only CO and oxygen. Now, for the case of the platinum catalyst, what you can see here is that for formaldehyde oxidation by itself, platinum is extraordinarily active. Even at room temperature, we got significant conversion, and by 400 Kelvin, we were essentially completely converting the formaldehyde. However, when we looked at formaldehyde oxidation in the presence of carbon monoxide, we found that the results were quite a bit different. In fact, we got complete inhibition, suppression of the formaldehyde oxidation until we reached temperatures where CO itself began to react. And there's really no surprise to this. CO absorbs much more strongly on platinum than it does formaldehyde. We have self-inhibition associated with the CO oxidation, and we have to get to temperatures where the CO starts to desorb and can open up clean sites on the surface before we can either react CO or formaldehyde. Now, in contrast to the platinum, what we found with the silver catalyst was quite different. Silver does not have this intrinsic activity that platinum does. In fact, this silver catalyst was much more highly loaded than the platinum. As you can see by the solid curve here, it's not as active as platinum for the neat feed. However, in the presence of CO, we find that the formaldehyde oxidation activity is actually better than that of the platinum catalyst. This is significant for automobile exhaust because you'll always have carbon monoxide around. And in fact, it's turned out that in practice on some heavy-duty GM methanol-fueled buses, the silver catalyst is one of the catalysts that has been the most attractive. Also, these results are not surprising for the silver either, because the weak, or if any, inhibition by CO is not surprising, again, because CO is weakly absorbed on silver, and we don't have that strong competitive absorption that we do with the CO on platinum. Moving on to copper chromium, it's much the same story as silver, the only thing being that copper chromium on the aluminum catalyst is not quite as active as the silver catalyst. In the case of rhodium, we find behavior that's much different than the platinum. Rhodium is very inactive, even in the case of oxidizing the neat formaldehyde stream. And in fact, CO oxidation proceeds much more readily over rhodium, well, somewhat more readily over rhodium than does the formaldehyde oxidation. And in the presence, in the mixed feed, we get an intermediate type behavior. Now, I've left the palladium to last because that's the most unusual or interesting behavior. And particularly in the case of the neat feed, what we find in this case is that the formaldehyde conversion starts to come up at low temperatures, much the way it does with platinum, but then we reach a maximum and then drop down into a deep valley, and then at higher temperatures again, the conversion comes back up. However, when we add CO to the feed, we get behavior that looks pretty much similar to platinum. Again, the normal CO inhibition that you do expect for these noble metals. Well, before I go farther and delve into the palladium a little more, what I'd like to point out is that, for the most part, these results are very similar to what we saw for methanol oxidation of the same catalyst. And in this figure, I show the same kind of results. This is older data, as you can see from the faded slide. But the curves are almost identical to what we saw, I just showed for formaldehyde. The one exception appearing to be the palladium, where we get the more normal behavior here. But actually, in looking at methanol oxidation over palladium, what we have found is that we see the same indications of the same kind of phenomena occurring with methanol oxidation as we do with formaldehyde. Here's some data that we obtained for 0.2% methanol, 1% oxygen over palladium catalyst. And you can see that the conversion comes up here and actually dips through a small local minimum. Now what we found And we wanted to do this with methanol because we didn't have the same flexibility in varying concentrations of the formaldehyde work. If we made the feed leaner, and in particular, in the next slide what I'll show is we reduced the methanol concentration by a factor of 2, and you can see here that the overall conversion curve for the methanol now has a much larger dip. And in fact, this is a consistent trend that we've seen in all the work. As we go leaner and leaner in these feeds for these small organic molecules, what we find is that over the plating catalyst we get deeper dips in these conversion curves. So this has led us to propose that in the case of the formaldehyde oxidation over the palladium, what is happening is that at low temperatures our catalyst is reduced, but as we go up and has a high activity, but as we go up in temperature, the catalyst switches over to an oxidized state, which is characterized by a much lower activity. And so we put together a somewhat simplified mathematical analysis of this to see if we could just fit this with a reasonable model. And the way we set it up is that we assume that the overall rate was given by the sum of the rates on a reduced fraction of the surface and an oxidized fraction of the surface. In an expression such as this, bimolecular Langmuir-Hinshelwood. And in addition to that, we assume that at each temperature and pressure, we have equilibrium between the rates of surface oxidation and reduction, given by a redox type expression here. We could then substitute those into the mass conservation equations and solve for the conversion profiles through the reactor. And again, showing the results here, this goes back to our data for formaldehyde oxidation over palladium, the symbols of the experimental. The solid curve is the predicted, and the dashed curve and the dotted curve here are the limiting cases if we assume a completely reduced surface and a completely oxidized surface here. As you can see, the top part, what it does is it tracks the fraction of the reduced surface as a function of temperature, and what the model predicts is that we get a fairly rapid switchover with increasing temperature from a reduced surface to an oxidized surface. I don't want to make too much of the model because there's a number of variables, at least 3, that we had no idea what they were and they were freely adjusted. But the point I would like to make is that the model seems plausible and the values that we put in do seem fairly reasonable. And also there's a lot of these 4 or 5 studies in the literature that point towards oxidation of palladium occurring right in this temperature range where we see the switchover on the catalyst activity. This is basically the final slide. What I'd like to point out from this work is that what it indicates is that you have to be very careful if you're trying to do developmental work for these methanol vehicles. And the results you get on a particular catalyst, such as the palladium, will depend very strongly on the setup of the vehicle, the air-fuel ratio, and that sort of thing. And I don't want to go into detail on this, but this is some comparison of some Ford data on a passenger car where they had a stoichiometric exhaust, and basically palladium looked very good there. In our own work with a heavy-duty methanol engine, which always runs very lean, we found that formaldehyde palladium-containing catalyst was very poor. So, in conclusion, we have found that formaldehyde oxidation parallels methanol oxidation over these catalysts. CO inhibits the formaldehyde oxidation over platinum and palladium, but not over silver and copper chromium. Formaldehyde and methanol oxidation over palladium is very sensitive to the oxygen formaldehyde ratio. Formaldehyde oxidation kinetics over palladium appear to reflect changes in the oxidation state with changes in temperature and feed composition. And although I didn't go into this, it looks like possibly the differences in activity and selectivity between the platinum, palladium, and rhodium catalysts appear to reflect differences in oxidation state. And finally, catalyst performance in real exhaust depends strongly on the exhaust stoichiometry and temperature. Thank you.
About what temperature did you find that minimum in these versions?
That's at about 400 to 450 Kelvin. And like I said, there are some references. In fact, one study in particular was done by Jaeger in Germany, and they did in situ X-ray analysis of their catalyst. And they could correlate oscillations in CO oxidation over that catalyst with changes in the surface from palladium to palladium oxide. And that was occurring right in the same temperature range as we see here.
Have you looked at any silver alloys for this vehicle?
I hesitate to say alloys. I mean, I think, as you know, we've looked at palladium, silver, bimetallic catalysts. And we do see promotional effects there, and we don't see any of these bad effects associated with palladium that we see here. So I would like to think that those catalysts, you know, the palladium in those catalysts is intimately associated with the silver, just based on that kind of data. But we have no direct evidence for that.
Could you comment on the effect of more refractory supports and maybe rare earth oxide promoters?
Well, aluminum is pretty refractory. I don't know. Sometimes, as pointed out in some of the earlier reports, you can get greater dispersion of your catalyst by going to rare earth promoters. In that case, maybe this oxidation reduction process may be more facile in smaller particles. But that, I'm just speculating there. I wouldn't expect to see tremendous effects.
Okay, we're going to move on and getting close.